Good morning. Today we are going to start our atmosphere notes part 5. We're working on the same hefty standard, but our I can statement for these sets of notes, this set of notes, is list and describe a global wind belt. And in order to understand global winds, we have to understand how the earth is unevenly heated. So I'm going to read you this paragraph as you fill in your notes, and then we're going to use two diagrams, which are also on your notes, to help explain what this paragraph is really talking about. Sunlight hits the earth directly in some parts and indirectly in other parts depending on the time of year. Now remember that a year is the time that it takes Earth to go around the sun. So because of its location around the sun, some parts get direct, some parts get indirect. Different parts of Earth point towards the sun throughout the year, and this happens due to Earth's tilted axis. A part of Earth pointing towards the sun receives direct light, while a part of Earth that is not pointing towards the sun receives indirect light. When sunlight hits a part directly, the sunlight is concentrated on a smaller portion of land. When the sunlight hits a part indirectly, the sunlight is spread out over a portion of land. So you might understand why this is causing uneven heating on Earth's surface. Alright, so here are the two diagrams. I really like how this diagram shows the different seasons as Earth goes around the sun. It also shows the tilt of 23.5 degrees. So if you notice, let's look at winter time. We have the equator right here, we have the northern hemisphere, we have the southern hemisphere. And if you look at the tilt of Earth's axis, you can tell that the North Pole is tilted away from the sun. Therefore, as Earth spins right here, the North Pole each day is not going to get direct light due to the tilt of Earth. However, the South Pole is going to be getting some light. Now, who's getting the most direct light? It would be right below the equator because that would be getting the most direct rays, sun rays. Whereas a little bit, probably like the United States, would be getting indirect light, and below the equator would be getting more direct light. That's all due to the tilt. So about 3 months later, we start springtime. Here, the tilt of the Earth is in the same direction, but because of that, the equator is now getting the direct rays. Okay? So before it was below the equator, during the winter time was getting the most direct rays. Now it's right at the equator. And that means that as we go further north or further south away from the equator, we're going to get more and more and more indirect sunlight. As we come over here 3 months later, we start summertime in the northern hemisphere at least. In the southern hemisphere, it would be winter time. So here you can see that the North Pole this time is going to be in sunlight as Earth turns and turns and turns, and this is why they have day pretty much 24/7 at this time. This is when Alaska would have the really long days, 20 hours of daylight, something like that, and 4 hours of nighttime. But here, right above the equator is getting the most direct rays. As you go higher or lower than that, you're going to get more and more indirect sunlight. And last but not least, we get to fall. You can't see the sunlit side of Earth in this diagram because the sunlit side would be on the opposite side of Earth right now. But remember that Earth keeps rotating around. The area on Earth that's getting the most direct rays would be the same as over here, which would be the equator. Alright, I hope this diagram helps explain a couple things. That Earth travels around the sun, this is a year in time, and that the tilt of the Earth stays the same throughout its revolution. Therefore, different parts of the Earth get direct light and indirect throughout the year. Here is a up-close diagram of either spring or autumn, and I can tell this because the tilt is not towards or away from the sun. In this diagram, it's probably pointing back towards the back of the screen or front towards us a little bit, but it's showing the most direct rays hitting the equator. Notice that all of these simulated rays are the same amount of sunlight. So it's not that the amount of sunlight that is changing, it is the concentration of the light on land. Here, the light is very concentrated in a small place. So that is going to be, all that light's going to be taken in by that area of land or water and turned into heat energy. So right above that, the air is going to be very warm. However, here we're getting a little bit more indirect, and down here we're getting a little bit more indirect, where that light now is spread out over a larger area of water or land. So when that water or land takes in the light, it is creating less heat per area in this area. Now, as you can tell, the South Pole and then the North Pole has got very indirect light, where the same amount of light is spread over a greater amount of land. Therefore, that land and water cannot produce as much heat energy in a certain area. So what does this all mean? Why do we care about the uneven heating in regards to talking about the wind? Well, if you remember, the uneven heating will cause varying temperatures. So obviously at the poles it's going to be much colder than at the equator pretty much year round. Therefore, the Earth also has different air pressures. Remember, talking about wet, water vapor, elevation, and temperature are the three things that affect the air pressure on Earth, above Earth. And so therefore, if we have different temperatures throughout the globe, then we're going to have different air pressures. And so if you remember latitudes and longitude, let's go over what latitude means. Latitude are the horizontal lines that go all the way around the Earth, and I think about it as you're climbing up a ladder, and so the latitudes go like this. And so at different latitudes you have different air pressures at certain times of the year. And because we have different air pressures, we know that the air is going to move from high pressure areas to low pressure areas. And this will create huge winds that blow steadily from specific directions over long distances. So this is the main difference between a global wind and a local wind. Local winds, small area, sometimes you feel them, sometimes you don't. If you don't, it's usually because the global winds are stronger. But these global winds are huge, strong winds that can blow steadily in specific directions over long distances. And because of that, we don't only have those little convection currents just over a small area of land, we have huge convection currents. And just so you know, convection currents can also be called cells. So, there's something weird though with global winds as well. We have something called the Coriolis effect. And what you need to understand is that if Earth didn't rotate, then global winds would blow in a straight path. So in this diagram over here, the yellow line represents, since we have the coldest temperatures would be the highest pressure here, and we have the warmest temperatures, which would be the lowest pressure here, wind would blow in this direction, okay? And so you can see the yellow represents how the winds would blow if the Earth didn't spin. But what happens is the Earth is spinning right underneath this atmosphere that we have above it. So because of that, the wind path actually gets turned to the right. So if you kind of put yourself upside down on top of that globe and you're thinking, okay, the wind's blowing this way and it's turning to the right. Why is that? Because the Earth spins counterclockwise. So as the Earth is spinning underneath that atmosphere layer, the winds tend to blow in that right direction, okay? In the southern hemisphere, it does the opposite, because here the South Pole temperatures would be coldest, so that's where your high pressure is, so the air is going to move towards the equator, and therefore they tend to turn left due to the spinning action of Earth. Now, in class on Wednesday, I think that's the day, we're going to do some demos, and so you can leave this part blank. Also, I'm not going to post the presentation until after Wednesday, but on that day we'll look at a short video on how water drains in the southern hemisphere, northern hemisphere, and right at the equator. We'll also check out a simulation of how pilots have to take into account the Coriolis effect. Alright, so moving on. On your paper you have a blank area. Well, it's not really a blank area. You have a picture of Earth with a bunch of lines and arrows drawn on it. And so what you're going to do is you're going to customize your map of the global wind belts. And here on your paper, notice it says include areas of high and low pressure. So the first thing you want to do is you want to put in the H's and the L's at the various lines. So at the very top of the globe, you're going to put H for high pressure. Again, we just talked about this on a slide back, and we discussed that it has high pressure because it has the lowest temperatures of anywhere on Earth. And then it's going to be, now these temperatures at this latitude compared to this will have the lower pressure. And then compared to that though, this will have the higher pressure compared to these. So it's kind of like you keep comparing them. So high pressure compared to this lower pressure, and then high pressure compared to this lower pressure. Again, starting from the South Pole, you'll have high pressure compared to this pressure, and then you'll have high pressure here compared to this pressure. This being the lowest pressure of anywhere on Earth, most likely. Now the next thing you need to put in is the latitudes. So you want to start and maybe put these on the left side of your diagram. So here next to the equator you can write 0 degrees. We're going to go up to 30 degrees north. Then we go to 60 degrees north. And then up at the very top it's 90 degrees north. Now going down from the equator, it's going to be 30 degrees south, 60 degrees south, and 90 degrees south. Keep in mind that we just labeled the main latitude lines, okay, as we talk about these global winds. Lastly, you're going to put the wind belts in. So notice over here I have the 3 wind belts that you need to include. The trade winds are going to go here right above the equator and below the 30 degrees north. But they also exist between the equator and the 30 degrees south. So it's almost like a mirror image where the equator is the mirror. So you have trade winds and you have trade winds. Now, you don't necessarily have to call them the northeast or the southeast trade winds. If you want to include that, that's fine. They're called northeast up here because the wind starts in the north and northeast and moves to the southwest. Here it's the opposite. Now, the next global belt, wind belt, is the westerlies. Longer name is the prevailing westerlies. They start in the west and move towards the east, and so that's why they are named the westerlies. Winds are named by the direction that they come from. And then they also occur from 30 degrees south to 60 degrees south. Last but not least, you have the polar easterlies. These are located between the North Pole and 60 degrees north, and the South Pole and 60 degrees south. And the last couple things that you're going to label are the calm areas. These are not labeled very well on this map. So here at the equator, this is your area called the doldrums. And what this means is that there's no wind horizontal. Remember, wind is defined as the horizontal movement of air. Here there is no horizontal movement of air. What there is rising air because it's all heated air. So we're going to be talking about that. But also, at 30 degrees north and 30 degrees south, you need to write in horse latitudes. So in these two areas, the air actually is sinking. So this is the part of that huge convection current where air sinks. And that is because it's cooling air. So we are going to move on later in studying a little bit more detail about